Okay, homework 12, problem 1. So problem 1 says, suppose that x is a WSS, and we're putting it through an LTI system, and the output is y of t. So the question asks us, if x is wide-sense stationary, prove that y is also wide-sense stationary. So just using some principles from signals and systems, we know that y of t is equal to the convolution of x of t with the impulse response of the system right here. And that's equal to this integral over here. So that's just some background. To prove that y of t is wide-sense stationary, we need to show that the expected value of y of t is some constant. And we need to show that the autocorrelation is a function of the time difference. So first let's start by checking the first piece, that the expected value is equal to some constant. So let's write the expected value of y of t is equal to the expected value. Well, what's y of t? It's just this integral, so it's going to be integral of x of t minus tau, h of tau d tau, minus infinity to infinity. Okay, so what we can do, because the integration and the expected value are linear operations, we can write this as, we can basically, we put the expected value inside the integral, but because x is the only one that's the random variable, we only have integral of expected value of x times h of tau. H is not a random variable. So we can write this as this. H of tau d tau from minus infinity to infinity. Well, we know that x is wide-sense stationary, so this is just some constant. I'm going to call it eta of x. And I can pull that out of the integral because it's just a constant. So we just get this times integral of h of tau d tau. Now, recall that the frequency response, capital H, is equal to, using the Fourier transform, is equal to this. Now, this piece here looks like this, but without the exponential. So what this is basically, we have the constant. This is the same as this when omega is equal to 0. Because we can't play with this t here because we're integrating tau, because we're integrating with respect to tau. But we can't set omega equal to 0. If we set omega equal to 0, we just get exactly this. So this is equal to h of omega at omega equals 0. This is just going to be a constant. So a constant times a constant becomes a constant. So we have shown that the expected value of y of t is equal to some constant. So this is good. But now we have to check that the autocorrelation is a function of the time difference. Okay, so this is just definition of autocorrelation. Y of t2. Okay. I'm not going to fit it on that line, so I'm going to come back down here. With expected value of the integral x of t1 minus tau, h of tau d tau, times integral x of t2 minus tau, h of tau d tau. Okay. So again, we can play around with these integrations and exchange the expected value with the integration. So first I'll just I'll just put these integrals, and I can write it like this. Let me just write it and then I can explain it. So I get this, x. And then we have, right, x. Actually, I wanna change this. I want this, just because these are like these two integrals. This tau is not the same integration constant as this tau, so this is actually wrong to write that they're the same. So I'm gonna call it a capital T, just to make it absolutely clear and correct, actually. Because these taus are not, this tau and this capital T are not the same integration constant. They're not in any way related. This is one convolution, this is another convolution. So, sorry about that mistake. So this refers to this guy, this refers to this guy, and then we have d tau, d capital T. And then we have this here. Okay, so now we can interchange the order of integration and expected value. So we can write, we have a double integral, and then we have, again, as in the previous part, these h's are not random variables, but these are. So when we take the expected value of this entire piece, we're only going to take this expected value because these are the only random variables. These are not. So we get expected value of x, t1 minus tau, x, t2 minus big T. That's the end of the expected value. And then here we have h of tau, h of big T, d tau, d big T, and these integrals go from minus infinity to infinity. Okay. This, we know that x is a is a WSS. I like to call it wuss because it looks like wuss. Expected, this is because x is WSS, or wuss as I like to call it. The autocorrelation, this is the autocorrelation, is only a function of the difference. So we get r xx, and then we have the difference of this minus this. So we get t1 minus tau minus t2 plus big T. Then we have h of tau, h of big T, d tau, dt. Okay. So then, this is what we're. Let me just write it again, and just rearrange these pieces in here. So we have t1 minus t2 plus big T minus here, and then we have this. Okay. We're integrating with respect to tau and big T, and we're integrating from negative infinity to infinity for both tau and big T. So after we're done with this integral, we will have successfully integrated out big T and tau. So what's going to be left is going to be this function, but it's not going to have big T and tau in it. What is it going to have inside? It's only going to have these two because we haven't integrated this out. We've integrated big T and tau out, but not these two. So in the end, the autocorrelation Ry of y of t1, t2 will still just be a function. So is only a function because this is, as we see, the tau and the big T will be integrated out, and the only things that are not integrated out are t1 and t2, and they're going to appear in this difference. So Ry of y, or the autocorrelation of y, is only a function of t1 minus t2. So we have proved number 2. Therefore, we have shown that y of t is WSS. So we have proven, therefore, that if x of t is WSS, then so is y of t. And that completes this problem.